So curls and divs tell us different things, right? Curl tells us how much it's curling, right? How much it's rotating. And divs tell us the net effect of input against output. Now, I hope that has helped. And if it hasn't, well, you can always just rub out the last 5 minutes in your brain, right? And you'll be fine. So here's the application. It is very intensive algebra, and it's a notation that once you get used to it, it's not too bad. But there is going to be like a cultural shock at the beginning. The curl of a vector field F, a 3D vector field F, is the cross product of the gradient operator, which is what this fella is called, with the vector function. And now the vector function F is going to be P, Q, and R, right? It's going to have xy plus x squared z plus sine of x e to the x, y. You know, it's going to have x, y's, and z in it. And when you put this guy cross product with that guy, this is what it looks like. Now, back in Calc 3, didn't you have to find the cross product of two vectors, for instance, to find the normal vector? Remember doing that? It's a while back. That's what's going to happen here. And if you take this, this is what the curl looks like. Now, do you see how messy it is? And it is a vector. The curl is a vector. That vector is essentially saying at any given point, what's the cumulative effect of all the little vectors near it? Is it generally pointing in one particular direction as a summation thing, right? As an overall pattern. The div is dead easy. It's a dot product of the two. And you take this guy here and you do a dot product with it. So can you imagine taking this guy and that, this guy and that, and this guy and that? So do you see an operator has a piece missing? And it's when you connect it to something that it becomes something that you can actually find. So I'll keep that guy there for a few minutes. But obviously you could wait until you look at the video and just pause it on that page and write it that way. Right, hopefully that's enough. Okay, ready to try this guy out? Now, how do you get, I think I should do that again, it's a bit messy. Let's suppose we have a vector function, xy plus z, xy z squared plus y, and x squared plus z squared, right? Suppose we had that guy. And I would like to calculate or find the curl of f. Now, the best way to set this up is the same way that you probably have, at least if you got me, you would set up the cross product. You do ijk, you put the operator for delta, so that's d by dx, d by dy, d by dz, and then you put, I'm going to call it function p, q, and r. Normally I won't write that down, but this case I will. So ijk, that's the same, that's your gradient operator, and this is your f. So in this particular question, it's going to be an ijk, the three partial derivative operators, and p is this guy, q is this guy, and r is this guy. So p is going to be xy add z. Q is going to be xy z squared plus y, and r is going to be x squared plus z squared. So you're going to get so many i's, take away so many j's, plus so many k's. This is just too big to fit in one. I know it is. That's why I'm going kind of on two lines. Okay, let's see what that looks like. That's the formula. Let's show you its application. If you want to get the I component, don't you cover up the I? And then you do major, take away minor. So in this case, you're going to do the partial derivative with respect to y of x squared plus z squared, take away the partial derivative with respect to z of xy z squared plus y. Okay, let's do each one in turn. If you differentiate this with respect to y, you get 0. And if you differentiate this with respect to z, you get 2 xyz. So that's your I component done. Okay, you want j, you do the partial derivative with respect to x of x squared plus z squared, take away the partial derivative with respect to z of xy plus z. And let's see what that gets us. 2x, and what's that, x, y plus z. Well, with respect to z, you just get 1. And that's your j component. And your k then, you cover this guy up in this direction, you get the partial derivative with respect to x of this fella, take away the partial derivative with respect to y, that guy. Let's see what that gets us. With respect to x, you get yz squared. Take away with respect to y, I believe you get x, and that's your k vector. And so the curl of f is 2xyz, comma, negative, this fella is what, negative 2x, negative 1. And this fella is y squared minus x, done. I think it lives up to its reputation of being quite intensive algebra, isn't it? A whole load of things being differentiated. Creating this is the key to doing those. This is a really messy formula. Unless you've got a photographic memory, you're probably not going to remember it. Even if you do remember it, there's so many fiddly bits, you're still probably going to have a hard time figuring it out. And these 3 bits are actually these 3 bits anyway, right? So you're still doing it. So this fella here, if I plug a point like 1, 2, 3, right? X is 1, Y is 2, and Z is 3. It will tell me what this vector field at the top here is like at that point. And it will be saying roughly it's pointing in that direction as a cumulative effect. Okay, so that was a curl. Let's show you a div, short for divergence. And it's simply just that guy, and that guy. Much easier to do. Partial derivative of this guy with respect to x is y. Partial derivative of this guy with respect to y is x z squared plus 1, added to the partial derivative of this guy with respect to z, and maybe now and again you're going to get some, collecting like terms or whatever. Would you agree finding the div is easy? Partial derivative x, add partial derivative y, add partial derivative z. Everybody's your friend, right? Easy done. Horrible, easy. If you plug in the number 1, 2, 3, and let's just do that an example. I wonder what the divergence of this vector field is if I looked at the point 1, 2, 3. Well, its value would be y plus x times z squared plus 1 plus 2 times z, and I'd get 9, 10, 11, 12. 12 and 6, I'd get 18. And 18 is positive, isn't it? So at that point in 3D space, isn't there an anti-clockwise rotation using the left-hand rule? So at that point, can you imagine that the object would be trying to curl round in an anti-clockwise way?
Isn't that the div though?
Oh, sorry, that's the div. Yes. The div, it's, oh, the div is just 18, right? It's, my apologies. Yeah. Although it's still positive, it is telling me something. That's telling me that there's a net leaving of information or the vector. So you can imagine the point 1, 2, 3, there is more stuff leaving than coming in. So positive in that sense is leaving, coming in. This fella here would be the vector representing the general curvature in an anti-clockwise direction. And that's a little bit harder for me to imagine. It's 3D, and 3D is hard. 2D I can think of as clockwise and anti-clockwise. 3D, my brain's beginning to hurt. So far, so good. Now, a very, very interesting property that we have met before, but only in 2D. F is a conservative field. Now, if you're a conservative field, don't you have that nice property that a line integral is 0 if it's a closed loop? Right. But really 2D. Right, what happens in the 3D world? Well, if the divergence of the vector field F is 0, 0, 0, in other words, if it is the 0 vector, you have a conservative field. And that means that you have a function called f, the potential function, that has that property. Just like we did in the 2D. Remember we did the potential function in 2D? You can expand that now to 3, 4, or 24. So a really useful property. You will get questions that says, is this vector field a conservative field? And that will become in your brain, I will find its divergence and it better be 0, 0, 0. And if it's not 0, 0, 0, it ain't a conservative field. Yeah, because I think yesterday, didn't we have the problem? All conservative fields have a closed loop in a closed loop line integral of 0, but not all closed loop integrals of 0 are conservative fields. Well, now we know how to tell which situation it is by finding the div of it. And I've just called that the div and nobody caught me out. Okay. Do another fella. When I get these guys ready, which one shall I pick? Oh, I've just done a polynomial. I don't want to do polynomials again. Right, this is like question 2. The vector field F is 8xy e to the z, 0, which is nice, yz e to the x. Okay. Let's do the div first because it's the easier one, right? If I call this P, call this Q, call this R, we do that guy. Partial derivative of this fellow with respect to x is 8y e to the z. Partial derivative of this guy, well, it's 0, so I guess it's 0. Of this guy with respect to z is y e to the x. We good? Right, now the ugly one. It's going to be I, J, K, the operator, and then 8xy e to the z, 0, and yz e to the x. So that's the setup that's going to allow us to calculate the curl. So, cover this guy up. Don't know why I'm dropping that down, don't need to yet. If you cover this guy, you're going to get this fella, take away that. So, major, take away minor. So what's that going to get me? It's going to get me that way, that. With respect to y is z e to the x. Doesn't matter, take away nothing. That's cool. Minus, get this fella. This guy, partial derivative with respect to him using x's is yz e to the x, subtract. Partial derivative of this guy with respect to z is 8xy e to the z, and that's your j. Underneath here, I'll do the k now. That's nothing. Take away this guy. And the partial derivative of this guy is 8x e to the z. So we are looking at the curl of f being z e to the x, yikes, negative z e to the x plus 8x y e to the z. And this fella here is negative 8x e to the z. There's lots of places in there that I could have screwed up. As far as you can tell, did I do okay? I know I'm doing the process right, but did I do the individual bits? I got a thumbs up, so somebody was doing it with me, says they got the same. I'm happy to call that good then. Really, it's kind of same old, they just are ugly. But I should try another one. What one shall I try? Well, I don't really have that many more of these ones to go before we've used up. I'll make up my own. That's good. Right, let's have f being, what will I have? Let's just do cosine y, no, x cosine y cosine z, and z sine x. Yeah. This could be interesting. So do this guy, partial derivative with respect to x plus partial derivative with respect to y plus partial derivative with respect to z. And let's see what we get. This guy gets me cosine y. This guy gets me cosine z. And this guy gets me sine x. Would you agree? Not a question you're likely to ask, but it's good to ask people questions just to get their brain moving. I can tell, looking at this, that the largest output stroke input that can happen, right? Divergence is measuring the net stuff leaving or stuff coming in. What's the maximum it could ever be going out?
Robertson?
Yes.
Aaron Tang in the chat asked if you could check the waiting room.
Thank you. I will do that right now.
Wouldn't it be 2?
I think you're close. I think he either disappeared or he got in, because I've got nothing waiting for me now. So, but thank you for telling me that. Hopefully, it's right. Someone said 2. I would say that it's possible to get more than 2.
Three.
Yeah. Couldn't all of them be 1? So the maximum outflow would be +3, right? So given this point, there's more stuff leaving than coming in, right? And the opposite would be -3. So whatever is happening in this vector field, can you think of it as like holes where stuff are being sucked in and holes where stuff are just miraculously popping out of? The most you could ever get in terms of numerical units here are 3 and -3. Now the scary one, this fella. And we are looking at the operator first. And then these guys. Okay, let's see what we get then. The partial derivative of this fella with respect to y is 0. Take away the partial derivative of this fella with respect to z. So you get 0, take away y sine z. If I cover this fella up, the partial derivative of this guy with respect to x is z cosine x. And the partial derivative of this guy is 0. Now we'll do the k's. The partial derivative of this guy with respect to x is 0. Take away the partial derivative of this guy with respect to y is -x sine y. So the whole piece together gives me -y sine z, -z cosine x, and -x sine y. And this measures in a vector right-hand draw. Do you know the thing where you go like this with your thing and it's what way is it pointing? Evidently there's a rotation going on, and the arrow that you get, which is a vector, is the center arrow of the rotation. Why on earth anybody in the engineering world would want to know that thing, but it's probably connected to torque. because everything seems to be connected to torque. Are we good? Any questions about that? Are we comfortable that, yep, I got another thumbs up, so I'm assuming I did it right. So let's look at a conservative field then and calculate its potential function. And I am not going to try and make one of these up because I'll never get it to work. So I'm going to pick a guy and I will do him. Okay. So this is question 7. And the vector function, because I'm basically just writing down what I can see in front of me, is y e to the negative x, e to the negative x, and it looks like it's 3z. So if this is going to be conservative, shouldn't its curl be the 0 vector? Agreed? So that's going to be P, that's going to be Q, that's going to be R. Let's find out if it is a conservative field. This one is y e to the negative x, this one is negative x, and this is 3z. Let's do the I one first. Cover that guy up. The partial derivative going this way of this guy with respect to z is 0. Take away this one, 0. Well, that's a good start. Middle one now. Partial derivative of this with respect to x is 0. Partial derivative of this with respect to z is 0. Try this one. Partial derivative going this way is e to the negative x with a negative in it. Take away, going this way, you get, okay, I'm not happy here. Why aren't my x's matched? Why isn't that killing off the other guy?
Don't we have to find the divergence of the curl?
Are we going to find, is your question, are we going to find a divergence?
Well, earlier when you wrote down to find if f is a conservative field when it becomes the 0 vector, I think
Yes.
you wrote down if the divergence.
Oh, I done that again. Yeah. Well, you change that div into curl and we're back to being good.
Okay.
My problem is I can't make that guy 0 and he better be 0. So I'm going to read the question again. It's y e to the negative x, check. It's e to the negative x, check. It is 3z, check. Oh, darn it in space. It is the correct answer. And the reason for that is that the question said, is it a conservative field? And the answer is, no, it's not. Right, let me get one that is a conservative field. So I'm going to look for one that says, prove that it's a conservative. Oh, shoot in space. They all say, if it is. That one looks promising. Yay, this one works. Okay, that is the correct answer. It is not a conservative field, so the answer goes in your box, does not exist, and it's finished. This next one is a conservative field because I looked at the solution. So this is question 9. And this fella is 18xy 9x squared plus 16yz and 8y squared. Are we good? Let me double check, because all I need to do is put a 2 in the wrong place and it won't be a conservative field. Okay, we are ready to rock and roll. This guy, according to the solution, is a conservative field.
Should we start roll soon?
Why don't you do that? Yes, do that right now, please. And give me a chance to set this up. Okay, we are ready to rock and roll. Let's get the first one. Partial derivative of this guy is 16y. Take away 16y. That's a good start, right? 0. Oh, by the way, see if it's one of those questions, is it a conservative field? If the first term isn't 0, do I really need to worry about getting the other two answers? Right, so you just stop there and say DNE. Right, so that's a good start. Partial derivative of this guy with respect to x is 0, and this guy with respect to z is also 0. So that's good news. Going this way, the partial derivative with respect to x is 18x. Take away 18x. We are rocking and rolling. I got the right answer. Now, we find the potential function. The left. So let's see how that's going to work. Won't this guy be equal to f, right? That's the property the potential function has. And this guy is the partial derivative with respect to x, y, and z. And it's going to equal 18xy, 9x squared plus 16yz, and 8y squareds. So you match first with first, second with second, and so on. So here's the first one. This is matching up the second one. And this is the last one. Now, we've had practice at doing potential functions. So hopefully this won't be that different. We're just doing it with 3 things rather than 2. So there is a little adaptation, but not much. If you integrate this fella with respect to x, don't you get 9x squared y? You agree with respect to x, 9x squared y. Now, plus an arbitrary constant. Well, the arbitrary constant is some function that doesn't have x in it. So that's just basically a placeholder. Now let's do this fella. Well, if the partial derivative with respect to y is this guy, if I integrate this guy with respect to y, I get 9x squared y plus 8y squared z plus a constant, and the arbitrary constant is some function that doesn't have a y in it, so I'm going to call that h of xz. And then we'll do it one more time. If you integrate this, you get 8y squared z plus an arbitrary constant, and the arbitrary constant is a function that doesn't have z in it, so I'll call it k of xy. Now the finish is you put this together. Now remember what it was like when it was 2, don't you just say, if you know, I'll merge them together into 1. Would you agree that that's one of your answers, and that there is the other answer? So when you put them together, you get 9x squared y plus 8y squared z, and we now have the potential function. Now you might think, what is that going to get used for? Guess what's coming? A line integral in 3D space, where your line integral is going to be passing through a 3-dimensional vector function f. And what will that line integral represent? In a lot of ways, it would represent the amount of work it would take to go from the start point, traveling along the curve to the end point. So when you're finished, you'll get a number that will basically be telling you, if I was driving my spaceship through 3D space, how much work would it take to get from the start to finish? But the cool thing is, if you know this guy, can't you do the, it only depends on where you start and where you finish? And it doesn't care how you got there. And if you're a conservative one, this works, right? And if you start at the same place and you zigzag around and you end up at the same place, won't the answer be 0 to the line integral? So what we've done is we've expanded the 2D line integral idea into 3D. So now we can find line integrals in 3 dimensions, at least for conservative fields. If it's not a conservative field, we can still do it. We'll just do parametric like we did before.